Okay, we're back. Okay, now if you'll recall, what we showed in the previous video was that when the altitude, that segment BD, drawn from the hypotenuse, drawn from the right angle to the hypotenuse, making a right angle, then what we've got were two new triangles formed. Okay, each of these triangles were similar to the original triangle, so the yellow is similar to the all-inclusive ABC, and okay, the green is similar to the all-inclusive ABC. Now what we want to show is that if they're similar to the all-inclusive, then they're similar to one another. So here we go with that, okay? So, so again, we showed here ABC and ABD, okay? So the yellow was similar to the all-inclusive. Here we showed that the green BDC was similar to the all-inclusive. And now we should be able to say by transitive property that, okay, the two new triangles, the yellow and the green, are similar to each other. That is to say, ABD and BDC are similar to each other. So again, we're going to take a look at the ratio of their corresponding sides, AB to BD, put that into a ratio, okay, DB to DC, and AB to BC. And as we can see, when we look at their ratios, they are consistent. So we've now shown, okay, that when this altitude BD is drawn from the right angle to the hypotenuse, of course, the altitude meaning it meets at right angles, then what we've done is we've created two new triangles, each similar to the original triangle, and, okay, each similar to each other. And now, okay, what we will show is this, okay? This is where we come up with the geometric mean, okay? So because the yellow and the green triangle are similar, we can set up a proportion that says BD is to AD as DC is to BD. That is to say that the altitude segment BD is the geometric mean to the two pieces of the hypotenuse that it created, okay? So the altitude BD, okay, is the geometric mean, which is saying it appears here in the numerator and denominator of this proportion, and it is the geometric mean with the two segments of the hypotenuse that it formed, okay? So BD is the AD as DC is the BD, okay? And so we had that going up here, okay? And so when we set that into motion, we cross multiply, we get BD squared is equal to the product of AD and DC. So BD is equal to the square root of that, okay? Which when we look at it with our computation proves to be 5.77, which is the exact measurement that it ends up being as illustrated here. And of course, even if I change this, this statement is going to hold true. So finally, we'll just look at the problem set that you have to do in this, okay? In the first section, of course, we're doing that geometric mean exercise that we talked about earlier, okay? Then this is asking us to set up the right proportions, okay, based on the similar triangles between the left and the right and the all-inclusive. Here we're doing, applying this new idea that in case here 6 is the geometric mean for the segment x and 4. So 6 is the x as x is the 4. 6 over x equals x over 4, and so on and so forth, okay? So of course you see here that x is the unknown, this whole length is 50, so the little length over here is 10, okay? We discussed these geometric mean statements here earlier, and then down here is doing some more of the same, okay? Trying to find the missing sides of this triangle. Of course, we're going to find y through the geometric mean idea, and then we should be able to set up proportions on the similarity of the triangles to find the other. Okay, so that is the completion of this, okay, which we is the ideas presented over here, okay, um, in, in conjunction with the geometric mean idea that that we had from Theorem 83. Okay, so that should do it.